Hello. Have you ever wanted to know how computers can do so many things at the same time? Like, how can your computer handle messages on Discord, play a video game, and remember like hundreds of tabs at the same time? Well, there's a lot of hardware that allows for this, but one important part is threading. Threading allows a program to split its execution onto a separate thread. You can think of a thread as another task that's running. As an example, say you had a lot of chores to do. You had to make the bed, you had to do the laundry, you had to clean the bathrooms, walk the dog, etc. If it's just you doing this, it's going to take a while because there's only one of you. So you can only do one thing at a time. But what if you could make a copy of yourself so that each copy could do each task and you'd be done way faster? That's the idea of threading. If you have a bunch of tasks that are going to take a little while to complete, then you can put them on separate threads and they can all be working at the same time. Threading is great for downloading large files, doing complicated computations, or just simple I/O. Like say you want to write something to a database. Well, you want to make sure that you're writing the right value. Quickly, before somebody comments, I do want to note that your computer can technically only have so many threads running at once. This is limited by your hardware. My processor has 12 cores, which means it has a total of 24 threads that can run at once. A computer will basically allow a process to run on a thread for some amount of time, and then switch to another process that's running on the same thread, and kind of juggle between all of the processes on that thread until, well, they're done. So that's why it seems like your computer can do so many things at once. But what does this look like in Python? Let's see how that works. All right, so before we start out, I want to say that some of this material is kind of referencing an article done by Real Python. I'll leave a link in the description to the article. It has some really great explanations for things, but I'm just going to kind of go over some of the code that they reference, and I've changed some of it to be a little bit more representative of what I do. So first things first, basic threads. So I'm just going to uncomment my block here, and then we'll run it. Well, I guess we'll go through it and then run it. So I guess second, we are importing a bunch of stuff here. We're importing threading, time, concurrent.futures, which we'll use later, queue, which we'll also use later, and random, which is just used to create random numbers. Not really a big deal. So here we can see that we have the main function. We also have this test function where it takes in a variable called a. This will then print that A has started, it will print that A has finished, and it will then print what the current state of the data object is. So we are then going to, within the main function, or statement, block, whatever, we're going to print that we are making some threads. We are then going to create thread 1 by calling threading.thread. You then give it a target function, so this could be anything. But in this case, it's our test function. And then you provided an argument. So this is the first argument, and that would be what A is. And then we are doing a second one, thread 2, where we're giving it argument 2. I will note that once we run this and kind of test this out a little bit, you can also specify something called a daemon. And if you make the thread a daemon thread, it basically marks it as not really important, so that if the program stops, the thread will also be stopped. Whereas if you do it like this, the threads will continue running even if you stop your program. Or at least until they're done. But pretty cool. All right, so we have our threads created. I then print that we have created our threads, and then we start them. So what is this actually doing? So we can see that we're going to print. We're then going to sleep. We're going to add our data, so the 1 or the 2, to the data object here. And then we're going to be done, right? We're going to print out this stuff again. Within here, we can see that we're going to, after we started our threads, we're going to post starting threads. We're going to then print the data, post joining threads, end of main, and then data. So before I play this or run this, leave a comment down below with what do you think the first output is be at the very end? What do you think data is going to have? All right, I'll give you a second. You got your comment? Okay, great. Okay, let's run this. All right. It was nothing, but you can see that it took a little bit. after we got to end of main, it didn't actually stop, right? We didn't get to this end point because we were actually sleeping in two threads. And these threads were causing the program to wait because the threads hadn't finished. And you'll also notice that data at the very end was still empty because we didn't actually append anything to data until after the end of our main function here. When we did finally finish, you can see that the values for data are actually 2 and 1. So that actually means that the second thread actually completed its sleep before the first thread. This could happen because both threads maybe are on a single like CPU thread, and it just happens that the computer decides to pick thread 2 before thread 1. So that could be why. But there's basically no guarantee that they would have a consistent order. If I run this again, it's possible that they could be swapped. Not the case in this case, but it's possible. All right, so that's awesome. But what if we instead join the threads? Now, what join does is it basically means that it's going to wait until the thread terminates. You might say that, aren't we already doing that? And yes, we are. So if we run this again, we'll see that we're still waiting. But it actually waits at the point of when you call join. So you'll see that here, we basically waited for thread 1 to finish, right? To finish its execution by calling join. Then we printed data. And then we waited for thread 2 to be finished by joining its thread to the main thread. And then at the end, we then have end of main, and we have now 1 and 2. So this will consistently have 1 and 2 in that order because thread 1 is always going to be finishing before thread 2. Yeah, pretty cool. Now, just to kind of show what I mean by if we have daemon, daemon equals true. Let's add this to both and see what happens. And I'll comment out these here. If I run this, it just gets to end of main and the threads are just kind of killed. They never actually get to finish what they were doing because they were considered daemon threads. And daemon basically, again, just means that it's like unimportant. It's part of the program, but it's not really that important if it finishes. There's like a technical term for daemon, but that's what you can consider it. Right, awesome. So we have finished with basic threads. So let's comment this out again, and let's go on to our next step, which is ThreadPoolExecutor. This actually comes from concurrent.futures. And what this does is it kind of manages threads for you to some extent. So in this case, we're going to do the same thing with a test function, but we're going to create a number of workers. And we're going to execute using this map. And what map basically means is it returns an iterator equivalent to map function iter. So we're just passing, again, this here. All right, so let's go ahead and run this. So we can see that thread 0, 1, and 2 have started. Then we see thread 3 and 4 have started. And then our final is 2, 0, 1, 3, 4. So you might notice that this actually blocked, right? We got to the end, but we didn't actually see done main until the very end, even though we were executing our threads here. Now, that's pretty cool. But another thing that's cool is we actually specified a max number of workers. So how many threads do we want to have happen at the same time? And what's the max for that number? This could be as big or as large, or as big or as little as you want. If it's less than 0, or I think if it's 0, it probably won't work. So a positive number sounds good. But in this case, it's great because you don't have to actually do anything to create a thread and pass it the arguments. You're kind of doing that. But to create a thread, make it start and make it join and stuff like that. This just kind of does it all for you. So pretty neat. So if you are going to use threads, I would definitely recommend you use the ThreadPoolExecutor over just creating a normal thread. Unless you're just playing around, then go for creating a normal thread. That's fine too. All right, on to part 3, race conditions. So one thing that you will encounter, I guess I'll leave that space there. When you are playing around with threads is that it is very easy to run into a race condition. What a race condition means is that you might make a change expecting another change to be complete. So let's go over the code we have here. So for this case, we're going to be submitting a thread. So submit calls the executed value with actually like a value that it's passing. To be honest, the distinction between submit and map are a little confusing to me. But for the rest of this tutorial, we're going to be talking about submit. So I would just use submit. If you know the difference, which I'm sure people do, leave a comment. That'd be great. It would help other people out too. Okay, so here we're basically creating this totally real database, which has this init function where we're setting the value to 0. We then create our ThreadPoolExecutor, and for index in range of 2, we are then going to submit, calling this database increment with our index. The index basically is just so that we can know which thread is running. So the first one will be 0, the second one will be 2. Now, within our increment function, we're going to try to do a read, modify, write, which basically means we're reading a value, we're changing the value, and then we're writing the changed value. So here we're going to say that the thread name is updating. We're then going to get the value from self.value. You notice that we're saying a local value here. Then we are changing our local value. We are sleeping for 0.2 seconds. And then we are setting our local value to self.value again. And then we're saying that we're done. All right, so let's run this. Here we can see, despite calling increment twice in 2 different threads, we actually still have the same value. Or actually, we actually have a value of 1, right? Even though it started at 0, it should be 2 because we called increment twice in 2 separate threads. But the reason this didn't work is because when we set local value to self.value, it is now in thread 0. It is now equal to 1. We'll say thread 0 equals 1. And then thread 1 equals 1. Okay, sorry. Okay, let me thread 0. Okay, there we go. Then at this point, for local value, it will then equal 1 and 1, right? But then we sleep and then we set the value. So no matter what, the value is going to be 1, right? Because we're always getting 0. And then because of this sleep, we're guaranteed that we're going to always just set it to 1. All right, so how do you actually do this properly? Let's go over that next. All right, locks. So locks is one of the great ways you can do this. So we now have our better real database, and we'll talk about step 5 or part 5 later. So our better real database, when we initialize it, we can see that this is basically the same. We're just referencing our better real database. Better real database it defines our value again, but it also defines this lock, which is a threading.lock. And what threading.lock is this basically a value where a thread can acquire the lock and basically unlock the lock for its own thread. It can then use that thread or use that lock for as long as it needs to. And then once it's done, it will release the lock, meaning that another thread can then acquire the lock. So that might sound a little bit confusing, so let's go over how this actually works. So again, all this is basically the same, but for increment, we can see that we basically have with self.lock, which will try to acquire the lock in this block, but it will also block when you can't acquire it, and it will release the block when it has been released. So what that means is that when thread 0 comes in and starts doing increment, if it's the first one, it will then acquire the lock for self._lock. When thread 1 hits this, it will hit this line and try to acquire the lock, but it will then be blocked. It will basically stop at this line and wait until the lock has been released. So then within this locked section, we are then getting a local copy, adding 1 to it, sleeping for 0.1 seconds, and then setting the new value. And then we're saying that we're finished our update. with lock, and then we're done. So this, when we run it, means that the fake database value is 2. So the reason, again, is because the first thread will be locked here, meaning the second thread can't get its local value yet, because, or the self.value, because it's waiting, right? If we move this to up here, it would still have the same issue because we're requiring it before the lock. So pretty awesome. All right, on to number 5, pipelines. All right, so the pipeline is kind of meant to, again, this is referenced a little bit, somewhat heavily from the Real Python. So check out their article down below in the description, because honestly, pretty awesome. All right, so this is supposed to basically kind of introduce you to a very common thing called producer and consumer functions or programs, you could kind of think of them. Basically how this works, there's a lot of code here, but it's pretty simple. Basically how this works is that for here, we're just creating a pipeline, and then we're creating 2 max workers, and we're calling execute, one with the producer and one with the consumer, and we're passing the pipeline. So when we create, or when we call the consumer, it is going to set a message, and then when the message is not the stop object, which is Jake is cool, then we are going to try using the pipeline that is referenced to get the message for the consumer. And then if the message is not the object, because we're updating it here, then we will basically print that the consumer is storing the message. So think of this as like storing, again, an object in a database. Now, producer is another function that mimics getting a message from the network. So in this case, you maybe have an API where you're getting something from one point or from like somebody calling your API, and then you don't have to store it in your database. You want to ensure that you can do that accurately. Kind of like the same case above where we added 1 to 0 twice and we ended up with just 1. It should have been 2. So in this case, we are going to, for index in range of 10, we are going to basically just create a random integer, and then we are going to print that the producer has got the message from the network, and we are going to set the message within our pipeline. So this is like we're trying to set it using this pipeline of whatever it could be. And we're setting this random integer, and after we've done this 10 times, we're going to set the pipeline object to this stop object, which means eventually the consumer should get this stop object and kind of break out of this loop. Okay, I think that makes sense. If it doesn't, I'm sorry, leave a comment down below and I will try to answer it as best I can. But let's go over the pipeline. So the pipeline basically mimics a pipeline that contains a single message that it can process at once. So say you're a person that's being handed a bunch of different papers. You can only look at one at a time, unless you're like one of those people who can like draw with both their hands or something. You can probably only look at one at a time. So in this case, when we initialize our pipeline, we set the message to 0. We then create a producer lock and a consumer lock, and then we immediately acquire the consumer lock. The reason for this, though, is because we don't want the consumer to be able to try and get a message when there is no message. So that means that when the consumer calls get message, it will hit this point where it tries to acquire the consumer lock. But the consumer lock has already been acquired, so it blocks here. Then when the producer calls set message, it will then acquire the producer lock, which is not locked yet, and then it will set the message, called the message, and then it will release the consumer lock. So now once the message has been set, now the consumer can actually acquire the consumer lock. So they're kind of swapping back and forth. Then the message will be retrieved, and it will then release the producer lock. So now the next message could be set. Now, it's important to do this first, because if you do this here, or just return self.message, it's possible that the next producer version was able to acquire the lock and then set the message again. So it's possible you could miss a message if you don't do it in the correct order here. All right, so now we have released the producer lock, meaning the next message can be set, but we already have our local version of the previous one, so it doesn't matter. And then we return the message. So that means we come back to here, we get our message. It is not the stop object, so we print out the message. But now the second value has been set, right, to message, because this is running in its for loop. So it sets the message to some other value. But now it has released the consumer lock, which means on the next loop of this, we can get the consumer lock. See how that works? So it just keeps flopping back and forth between the consumer lock or the producer lock being acquired or locked or released. And we're slowly getting all of the messages. All right, let's run this and see how this works. So in terms of output, we should see that some producer messages might be added first before we ever even see this consumer storing message. But that doesn't necessarily mean that we're losing any messages. So let's see. Okay, we got a lot. Let's scroll up. Okay, first thing we see is making some threads, classic. Then we see producer got message 23. So, oh, sorry, I'm scrolling around, struggling. Producer got message 23. Okay, that's great. Then it's setting the message, which means we are then calling this, getting the producer lock. We then set the message within the pipeline. Then it says producer got message 75. So then we reached here, but we can't acquire the producer lock again yet because it hasn't been released back up here. So the next message will be 75 after 23, but we can't really set it yet. All right, then we have the consumer storing the message because the consumer has called getMessage, acquired the consumer lock, which has been released during setMessage, and then it gets the message and releases the producer lock. So we basically have 23 by the producer, the consumer is getting 23, producer is setting 75, the consumer is then getting 75, and so on and so forth until all of the messages have completed, at which point the producer will set the stop object, which is Jake is cool, and then it will result in the consumer finishing, at which point there's nothing more for the threads to do, so the threads exit. I know, it's maybe a little bit difficult to check out, but I'm going to leave a link in the description to the code for this as well. So feel free to just download this code and try it out yourself. If you leave it in the current state, it's safe. If you change some stuff up, it's possible you might end up with some kind of process running in the background. But just go to the task manager and kill anything that's related to Python, and it'll probably be fine. All right, let's go ahead and go to number 6, which is the mostly last one. In this case, we can use a queue. So a queue is basically a list. Simply, it's kind of basically a list. That's what its underlying data structure is. But what a queue allows you to do is get the first message, right? It's like a first in, first out, like you're lining up at a bank or grocery store or something. So the first person who enters should be the first person that gets helped, unless you have like people who are butting or something, but we don't have any butters in code. So in this case, let's go over all of our code. Now, I know this is going to look like a lot, but the reason that a lot of this is actually here is because we have this pipeline, which is basically just using a queue. So it's implementing a queue. It's extending a queue rather, which means it's just kind of wrapping some of the stuff that a queue can do. You could just make this queue, but we're not going to get any of these get or sets. So that's the only reason that it's there. All right. So we still have the consumer and we have the producer, but they look a little different now. So the reason they look different is because we have this event is set. What is event? So event is something that we can pass called a threading event. And this can be just basically an object that you can set within the context of a thread. It could just be, you could think of it as like a Boolean or something, but it's basically a class that allows you to set a flag that is true when set is called, and you can call clear to make it false. And then the wait method blocks until the flag is true. So it's kind of like a lock, but in this case, it's an event. All right, so we call our producer with the pipeline and the event again. And this time we're going to sleep for 0.1 seconds, and then we're going to set the event. The reason for this is because this is the way that we're basically telling our program to stop. Otherwise, it's just going to continue to make messages. So that's why we want it to stop within 0.1 seconds, because it can do a lot in 0.1 seconds. All right, so our pipeline here has get message and set message. Very simple. It's just getting the value from the queue, so the first message, and it's returning it. And set message is putting the value into the queue. Now, you might be wondering, where are our locks for our queue? Well, a queue is actually something that's called a thread-safe implementation, or a thread-safe class, which means that it handles all of the locking by itself. Even if you're not doing this in a queue, technically the main thread is kind of a queue, but all of this is already safe to use within a queue, or within a, sorry, not a queue, within a thread. Thread queue, there's so many words going on. But yeah, so if you want to use a queue within a thread, it is safe to do so. Within multiple threads, it's safe to do so, because it's going to do all the locking for you. Again, these are only here just so we can kind of see when things are being printed. All right, so our pipeline, our producer rather, takes in our pipeline an event, and when the event is not set, it's going to create a random number, and it's going to set the message. This means that it's going to add a new number to our queue, because set message will basically put the value into the queue. Awesome. So it's just going to while loop, keep doing that until the event is set. The pipeline, or sorry, the consumer, I keep saying pipeline, will basically pretend that we're saving numbers to a database. So while the event is not set, so the exit case, or the pipeline is not empty, because we don't want to miss things that are on our pipeline, and empty is just like, are there things still in the queue? Then we're going to get the message from the queue. Consumer, we're just passing as like the name, I believe, just so we can print that off. And then we're going to basically print kind of saying that like, this is what the queue size is, this is what our message was. But this is where if you were actually doing things with a database, you would maybe put something into the database or something like that. Then finally, once our pipeline is empty and our event has been set, we will then exit. So I'm going to run this. We're going to get through a lot of things here. One thing I should mention. When we create our queue, we set it to a max value or max number of things as 10, meaning that we can at any time only have at most 10 items within our queue. That means that if something gets pulled out of the queue through the get, now there are 9 items and now there's room for one more. So that means that this put will be blocked until there's space, basically. Okay, so we'll run this, but we're gonna kind of have to look at some of the, well, we'll see. All right, so we see a lot of stuff here. Let's see if we can find the start. Actually, no, let me run this again. All right, and let's go to the very start. Yeah, see, there's too much output. But basically, we can see here that the producer about to add 39, the queue size, producer added 39. We can see the queue size here. The queue size is kind of always 0 because the consumer is able to consistently get values from the queue. And then we can see at the very end, if I keep going down, that eventually like the queue size did reach a 1, which meant the producer was able to put in more things than the consumer was able to handle. And then we finally get to the point where the consumer, you see a lot of consumer messages because the consumer, like the producer received its exit event, which because the event was set, and then the consumer gets things from the queue and stores them. If we want to see like a shorter output for this, one thing that we could do is make it so that, oops, what did I just do? Make it so that we do time.sleep for like 0.1 seconds here. And if we do this, it means that the consumer is going to pull things off of the queue more slowly, which means that there'll probably be at max 10 things on the queue at one time. So if we do this, we can see that we did actually reach 10 things on the queue because it was taking time for the consumer to pull things off. So we see the producer basically added a bunch of things to our queue. It got to the end there. The main set the event to be set, and then the consumer now is able to start getting things because it also slept for 0.1 seconds. So if we made this like 2 seconds, we can see that it's like pretty similar, but a lot of producer stuff, the main setting, and then we can see that the consumer was able to start getting things from the queue before this was the main set the event. All right. So in this case, we're able to have our consumer slowly take things off of the queue. And once it's done, it also exits because the queue is empty and the event is set. Pretty cool. Now, as a final little fun example, well, kind of simple example, but fun example, I have this here. So say we want to basically download a bunch of YouTube videos or something like that. All of my YouTube videos. You could simply do this by, having a list with a bunch of URLs or whatever the resource value is, and then just call whatever the API is and just start downloading them. There is a pit package for this, by the way. And if we were to do this individually, it would take a while because YouTube videos are big and it can take a long time to download them. But if we do this with a queue and with some, say, workers, meaning threads, we can actually do this on multiple threads, meaning we can download multiple things at a time. You're probably going to be limited by your internet speed at that point anyways, but it's possible that, you're going to be able to still download more quickly by doing this on multiple threads. So in this example, we have our download queue. We're just setting 100 values within our queue. We never set the max number of values that can be set. Then we're creating our ThreadPoolExecutor with 2 workers. And then for our 2 workers, we're going to submit with this download file, meaning our 2 workers are each doing the downloading. We're setting the value of the index, basically which one are we here. That's just this here. And then the download queue. So our download file will then say, while it is not empty, we're going to get the value from the queue. We're then going to sleep for 2 seconds, pretending it's downloading something very quickly. And then we can see what we get here. So if I run thread 2, we can see it's taking the 0.2 seconds, but it's doing everything here. And eventually we should get to handling 99 and it will be done. All done. Pretty cool. But you'll also notice that main done is like way up here, right? It finished 17, 18, 19 before we even got to main done. So pretty neat. That's threading. I know it might be a little bit confusing, but it's super, super powerful if you're able to learn how it works. I will just mention really quickly that there are some other things that are actually mentioned in the, let me go to this site here. And if we go down here, there are some other things that I think are mentioned here, such as semaphores and timers and barriers. Semaphores is the really big one that I would really mention. And basically what a semaphore is it's kind of like a lock, but it allows you to set a specific number of locks that can be acquired before it blocks. So this can be super great if you want to, say, allow a lock that can be acquired or unlocked. You can think of it as, like 5 times. But after 5, we don't want to have any more than 5. Then any time it's released, then another thing can acquire it. And then once it's been released fully, then, 5 new things could, or however many. So that's a big one here. Timers, basically you can call something on a thread using a timer. And barriers kind of like block things from running. They're a barrier. But yeah, take a look at this article. It's super useful. And download some of the code that I have on GitHub. And yeah, play around with some threading. Thank you again so much for watching. Please drop a like down below and consider subscribing. And I'll see you in the next one. Remember, I'm Jake. You're awesome. This has been Threading in Python. Cheers.